Welcome all, and welcome to my talk that's either called Chasing a Wheel Down a Rabbit Hole or 10 times smaller Docker images for data science. Right, so I actually have a PyData global slide in here that we don't actually need. So about me, as Ruben already said, I'm actively involved in the PyData ecosystem. So I'm the co-chair of PyData Amsterdam and the vice chair of PyData Global. At work, I'm responsible for training and educating junior media data scientists in a bunch of different topics. And I like to do some open source. So Scikit-Lego is a package I maintain with Vincent, who was here yesterday. And time series is something that I recently started to do Bayesian hierarchical time series estimation. But that's not what we're here today. We're here today basically because of this tweet. It popped up on my timeline like a couple of months ago. And Jason here asked, if you try, how small can you get a Docker container for the PyData stack with like pandas, NumPy, Scipy, and friends? And that's sort of an interesting question in and of itself. But he asks, like, how small can it reasonably get? And that always triggers me because then I'm also curious about how small can this get if you let that reasonable constraint go. And that led me down a rabbit hole, and this question intrigued me. So today I'll be sharing my search in how small can we get a Docker container for the PyData stack. And this entire question is kind of ironic because, well, whales don't really fit down rabbit holes in the first place. Anyway, what are we talking about? Let's say we have a model training container, right? So we have Matplotlib maybe to do some plotting at the end. We use NumPy, we use pandas, we use Scikit-learn. Basically all the regular PyData stack stuff for training machine learning models. Those packages have some dependencies of their own. So this then becomes our complete requirements file that we have for our Docker container. That's the things that we need in our Docker container. And a very basic, just straightforward run-of-the-mill Docker file to build an image based off of these requirements would look something like this. So we pick our base image, Python 3.8. We copy in our requirements and we pip install those. And we copy in the rest of our source code, of our application source code. And then we install our package and we run some kind of test to see if everything works. And this works fine. But if you build this, you suddenly realize why Docker chose the largest mammal on Earth as their mascot. Because this image is 1.7 gigabytes. And for a very simple Docker container with some Python stuff, that's actually quite insane. So Jason's question was very relevant. Like, we should probably think about how we can make these smaller and where do we start? And the thing I always want to start with is like the main step one is always to think about what your application needs. Do we actually understand what our app needs to run? Do we know what third-party tools it needs, what third-party tools it doesn't need, what kind of development libraries are needed and that might get installed, but maybe we don't need them? All those kinds of things. Because, for example, there was this copy ... which just copies the entire working directory of our Docker, of our project into the Docker image. And I'm not sure about you, but like a typical project I do at a client has a folder structure that looks something like this. We have a Git folder where our entire Git history is in. We have an IDE folder that contains random settings for our development environment. Maybe we have some local data. Maybe we have some locally trained models. But more importantly, we have a virtual env in there that has all our dependencies. So if we do a copy ... all that stuff gets copied into the container as well. Whereas we're going to install new dependencies in the container, so we definitely don't want our local virtual env in there. So let's just start with not copying those kinds of things in. And the tool for that, is a Docker ignore file. And the Docker ignore file works very similarly as a git ignore file, in that it basically gives a list of things that you don't want to be copied in the container, even if you do a copy ... So what you see here, for example, the .git folder, we don't need that in our container. We don't need the virtual env in our container. We don't need data, models, notebooks. Maybe we also don't need tests in our container, right? That's a bit of a personal preference, but some people say, no, for production use, I don't need my tests to actually be in there. And that can save some size as well. So when we add this Docker ignore file to the root of our project structure and we rebuild it, we see that indeed this already slims down our Docker image size quite a bit. 1.7 gigs down to 1.3. Basically, we shouldn't ignore the Docker ignore. But then, right, what is the next step? Probably we need to figure out where most of the size of our Docker image actually comes from, right? What is making our Docker image this big? And to do that, we can run a command called Docker history. And we can run Docker history on an image name, and it will list basically per layer in that image what it was created by and what the size is. So when we look at this, we see 360 megabytes that came from our pip install requirements. The rest is kind of small, except for like the base image, the from Python 3.8, which adds almost a gigabyte. And that brings us therefore to step 2, which is use a smaller base image. Right? Most of the size of our image now comes from our base image, so that's probably what we want to tackle first. And a good, reasonable first step there is to, instead of use Python 3.8, use Python 3.8-slim. And the image is based on Debian as well, just like Python 3.8. Python 3.8 is based on Debian, but it uses the slim version of Debian. It doesn't actually change anything about the Python installation on the image. It just makes sure that there are less like commonly used packages that are installed in regular Debian, but aren't installed in this Debian Slim, so they aren't installed in Python 3.8 Slim either. And the only thing we actually need to do is add this -slim to our first line. And rebuilding this gives a much more reasonable 489 megabytes of disk space. And that's a huge difference for not a lot of work. So I would always recommend use Python 3.8 Slim, except if you have a very good reason not to. But right, so the base image of Python 3.8 Slim is about 180 megabytes. So that means we have still like 360 megabytes from other layers, right? And we already saw in the Docker history command that mostly stemmed from this pip install requirements.txt. And what we now might want to do is figure out what are those 350 megabytes? What is in there? Do we actually need all of that? And my favorite tool to find out what's actually driving up the size of our Docker images is a tool called Dive. And Dive is a terminal UI. And this terminal UI will basically allow you to look through the layers and look through the file system corresponding to those layers. So what I have in the left here is the top left. Basically, here are all my different layers in my Docker file. And I can go through them. And I can see like what's the ID, the hash ID of the layer, what is the command that made it. But I can also see on the right here, like what did it actually change, right? So this pip install requirements file actually added like 318 megabytes in the root and 87 megabytes in this user folder. And if we look at, for example, what is in this root, we will find that 72 megabytes are added by a cache folder, where there is a pip folder, and it basically caches, apparently, some HTTP requests. And if you think about it, that's not really needed. Because what pip does is when you pip install something, it indeed caches those packages somewhere on your disk, so that if you need them next time, you don't have to re-download them again. But in this Docker container, we're not going to reinstall pip packages. So we don't need them cached, and we could probably just get away with this. And very similarly, in this local lib Python 3.8 side packages, this is where we see where our actual packages are installed. And we could look around here as well and take a look at like where are these megabytes coming from? And for example, there's some interesting things. If you look at the Matplotlib toolkit, in the tests folder, there is 3.5 megabytes of base images. And probably we don't need those either in our Docker container. And there's also PyCache files, which we probably don't actually need in our container either. And like there's some packages have docs in there, which also can have a lot of images and HTML files or JavaScript that we also don't need to actually run. So the next step that we want to probably do is remove all those unneeded files. And something that we could try to do, for example, is just run some commands to actually delete them. So after installing our requirements, in the highlighted block, you see that we try to delete the pip cache folder, and we use find to find like text files, markdowns, images, all those kinds of things that we're not going to need, and remove them from the side packages folders as well. And if we then build this, what we actually find is that it made our image bigger, right? We went up from 489 megabytes to 503. So why didn't this slim down our image? Essentially what happens is that every statement in a Docker file makes a new layer, and each layer can only add information, and they don't interact with each other. So the way that data gets deleted, or that files gets deleted in next layers in a Docker file, basically is that they mark certain files with a tombstone saying, act as if this file is deleted, without actually removing the file from previous layers. So how this looks for our image is that we take from Python 3.8 Slim, which is 13 megabyte layer, and it gets all compressed, like the file system contents get compressed in a tar. The copy requirements.txt adds a couple of bytes because it adds this requirements.txt, and then the contents of the requirements.txt get tarred as well, and we store those as a separate layer. Pip installing them adds this cache folder and adds this side packages folder, and all the content will be in another tar. And then we can run our mrf root cache pip afterwards, but what we actually see is that it just marks files for deletion. It doesn't go back and change our previous layer tar. And the same thing for that big find statement. And then the actual size of our image is the combined size of all these different layer tars. So even though we delete stuff later on, it's still going to be in our image. Which brings us to step 3, which is use as few layers as possible. What I typically do is I sort of develop my Docker files in separate blocks, but if possible, combine them later on. So don't create unneeded files and those kinds of things. What that looks like for our image is basically, rather than having separate run statements, we do it all in one single big line. Right? So we pip install the requirements, and then on the next line, well, in the same run statement though, we double ampersand to run the find, the big find statement and delete those. We do the same thing for the PyCache folder. And already in the pip install, there's an option that says no cache there, which makes sure that we don't get this pip cache thing. In this way, we once again shave off quite a bit of data. Right? We didn't delete anything that was necessary for our container to run. We just deleted cached stuff and tests and those kinds of things. And this way, we're down to 326 megabytes. And now we're starting to get in more serious territory of disk space saving. If you don't want to do this manually, by the way, if you don't want to compress all your statements into a single run statement, Docker recently introduced a squash option when you do a Docker build. And then what it basically does is it creates one single image at the end of everything. One single layer out of your image at the end of everything. So it squashes all your layers for you. Right. So now we're at 325 megabytes. And now we're starting to get again in the space where our base image is taking up a large portion of our space, of our size. And if you've talked to people about making small Docker images, probably you will have gotten the recommendation, just use Alpine as a base image. Alpine Linux is indeed very tiny. And if we look at like the Python 3.8 Alpine version, we see that it's literally only 5.5 megabytes. And using Alpine, you're told, will make your images smaller and it will speed up your builds. So let's go ahead. Let's go and try that. When we change our basic Docker file from Python 3.8 Slim to Python 3.8 Alpine, so we change again the first line there, the from statement. And when we go and try and build that, we run into an issue, right? We get a command errored out with exit status 1, Python setup.py egg info. And if we then scroll through the logs and compare the differences between our images, like between the Python 3.8 and the Python 3.8 Alpine, this is what we see. So in the top here, we have the build log from installing Matplotlib in Python 3.8. And on the bottom here, we have the build log from installing Matplotlib in Python 3.8 Alpine. And what we see is that there's only like a slight difference. The last line is different, right? Because whereas in Python 3.8, we're downloading a file called matplotlib 321 something something manylinux.whl. In the 3.8 Alpine version, we are downloading matplotlib 3.2.1.tar.gz, right? And this is the only thing this is the first thing that's different. And then from here on out, things crash. So what's going on here? It turns out that there's these things called wheels. And wheels are certain distributions of Python packages. And it turns out that the wheels that there are on PyPI are not compatible with Alpine. So what is a wheel, and like why doesn't Alpine use them? There's different ways in which we can ship Python packages. And for most packages, it doesn't really matter, but for a large portion of the packages that we use in data science, it does. Because most packages that we use in data science don't just use Python, right? They're so-called extension packages, which means that they rely on C as well. Which means that we need a compiler to actually compile that C code before we can run it. And we probably have third-party C dependencies that our packages depend on, like BLAST dependencies, for example, for NumPy, that need to be in place before we can compile against them. So if we get source code, we need to compile it. But if we get a wheel, we apparently don't, because wheels are a binary distribution format. So it's already a built version of our Python package. And because it's pre-built, we don't need to do any compilation steps. For example, if you look at pandas, there's two ways in which we can build a shippable image, a shippable package out of this. We can run Python setup.py sdist on the left. We can run Python setup.py bdist wheel on the right. So the sdist on the left stands for a source distribution. And when we look at the source distribution, what we actually see is that it's just a big tar, again, with all the source code of pandas in there. So especially in the libs folder, for example, you see algos.c and algos.pxd and pyx. Whereas on the right, in the wheel version, those are replaced with certain shared objects, these .so files. And that basically means that in our wheel, they are already compiled for us. So when we install a wheel, we don't need to do those compilation steps ourselves anymore. And so why are they then incompatible with Alpine? Like, why doesn't Alpine use these wheels? It turns out that Linux has a lot of different flavors, and each flavor can be slightly different, meaning that compiled stuff on one Linux flavor might not work on another. So what the writers of the wheel PEP thought of was, let's define a standard subset of functionalities that we can expect to work on many different kinds of Linux installations. And that subset is called many Linux. And part of that subset is that everything should be compiled against a certain standard library version of the C standard library, namely the glibc implementation. And it turns out that Alpine doesn't use glibc. They use something called Moozle, and it's slightly different. So if we want to run C extensions, Python with C extensions on Alpine, they have to be compiled against Moozle. But since that is not part of the many Linux spec, the wheels that are on PyPI aren't compiled against Moozle. Basically meaning we have to compile everything ourselves. And to compile things, we need to have certain build dependencies in place. And it turns out that for the packages that we have, the most important ones are free type dev, and libp and gdev, which are dependencies that Matplotlib needs, and OpenBlastDev for NumPy and Scipy and the likes. And then G++ and MoodleDev are just more standard dependencies that we need in any case. And there's another interesting side effect here that so these dependencies are kind of enough to actually install all of our stuff. But it turns out that if we have scikit-learn in the requirements.txt, it doesn't work either. Because scikit-learn, when you run the setup.py, actually already expects NumPy and Scipy to be installed. But what pip install does when it installs a list of packages, it first runs all the setup.pys and then goes and installs it. So you get this sort of bootstrap problem where you need to install NumPy and Scipy first, and then you can only install scikit-learn. Right, so we have our build dependency into place, and when we build this, it will work. It does take a bit of time though. Building this image, the first time took almost an hour, like 59 minutes and 31 seconds. And it actually made our build bigger again. So using Alpine will speed up your builds, will make your images smaller, is not necessarily true. Because in this case, we obviously see that it's not that simple. But there's still probably some leeway that we can get here, right? Because what we did was we installed all those build time dependencies, whereas we don't really need them in runtime. So probably we should try to remove those build time dependencies from our container. And something that you could try to do is just delete some of the build depths after you've installed everything. But we've already seen with like how the layers work and the tombstones, why this won't work, right? So you might be tempted now to say, okay, let's put it all in one single line, like one single layer. But with the build times that we're talking about here, with these hour-long builds, you kind of want this Docker image caching, this layer caching to work, because otherwise speed of iteration is just going to be absolutely terrible. And thankfully, there's a nice feature that's possible to use here that sort of gives you the best of both worlds. And those are called multi-stage builds. If you so what you can do in one Docker file is have two different images. We can have a Python 3.8 Alpine image as a builder and a Python 3.8 Slim as a runner. And what we can do in the builder image is make sure that we have all the dependencies into place. And in the runner image, we just need to copy the installed stuff from the builder image. So we go through the same motions in our builder, but in our runner, we just copy from the builder, from the installed packages in the builder, and we only install the runtime dependencies, OpenBlast and FreeType in this case. And that brings our size down significantly again, 487 megabytes. And we're not below the Python 3.8 Slim yet, but at least it gives us some indication that we can probably still continue, right? There's still merit to this road. And so one of the things that you might ask yourself now is that why did we still need OpenBlast and FreeType? Because we could build our own wheels, right? And we didn't need OpenBlast and FreeType on Python 3.8 Slim. So why do we need them on Alpine if we're building wheels anyway? And that's actually true. But something that we need to do manually, though, to make that work is fix our wheels. So when we build a wheel with pip wheel, we just compile everything and put it in a wheel file. But there's a tool called audit wheel, which we can use to check whether our wheel is many Linux compatible. And not only that, it actually also is able to fix your wheels to make them more many Linux compatible. So if we look, for example, on an Alpine built version of NumPy, and we run audit wheel show on it, it will tell us that there are external shared libraries required by the wheel, namely Moozle, GCC, and OpenBlast, and libstd C++. And what it can now do is when we run audit wheel repair, it can take those shared dependencies and actually copy them into our wheels. And when we do this for all our packages, by just finding all the wheel files that we built and repairing them, and then copying those installed wheels into our runner image, it turns out that we can do away with the OpenBlast and FreeType dependencies in our runner. And then we're already at 288 megabytes. And this is kind of cool because now we built the Python 3.8 Slim benchmark. And now it's just a matter of squeezing out whatever we can still get. And if you've worked with C or C++ or anything in the past, you probably know that if you're compiling your packages yourself anyway, you might want to try adding some compiler flags. Because even though we can't partially install Python packages, we can ask the C compiler to make the C dependencies of our Python packages as small as it possibly can. By, for example, giving it an optimized disk space flag or a remove debug information flag. And if we try that on Scipy, we actually see that the size of Scipy goes down from 35 megabytes to 26 megabytes. And there's probably some other flags that you could play around with, but these were the ones that I found to have the biggest effect. And adding these to our build steps is actually quite straightforward. We just have to set a cflags environment variable before we run pip wheel to tell it, please optimize for disk space and remove all these debug information stuff. And that removes another 50 megabytes. So we're getting very close now to a 10 time size decrease. So let's dive in once more into our image to see what is causing this last bit of data. So this is the image that we just talked about, and if we go to the root folder, to the Python 3.8 folder, what we can, for example, do is still look at what is taking up most space in our image. And something that you might see that wasn't there before is this scipy.libs folder. And that is actually the libraries that came from this wheel repairing stuff. And if we open that, we see libopenblast that takes 30 megabytes. The thing is, though, that if we open NumPy-libs, that we also see libopenblast that takes 30 megabytes. And the file names are the same. And actually, when you compute the hashes on them, they are also the same. So these files are exactly the same. They're just duplicates in our image that we don't actually need. So that's sort of the last thing that we probably want to get rid of. And something that we can quite straightforwardly do is delete the NumPy version of libopenblast and make a symlink. So this ln-s makes a symlink from the Scipy libopenblast to the NumPy libopenblast. We can't do this for only libopenblast. We can do this for all these shared object libraries that we actually needed. And when we do that, we end up at a Docker image of 188 megabytes. And that's actually where I got stuck. And this is the smallest that I was able to get this Docker file. Should you do this though? Right, on the left, we have a 326 megabyte image that built in less than 5 minutes and just works. Whereas on the right, we have a monstrosity to do all the things that we described up until now. It builds in way over an hour. Yeah, it's like half the size, but still, probably not worth it. That said, I do hope that some of the things in here at least made you think about how do Python packages actually work and how do they get installed and how does that work in our Docker containers. And stuff like removing cache files is easy and we should probably do that. And stuff like sharing external dependencies is maybe less easy, but it also is not very risky and that part doesn't take that long. And we might actually do want to do that part. So in conclusion, when you want to think about small Docker images, think about your application's needs first and make sure you thoroughly understand them. This trip learned me a lot about wheels and how that entire process works. And I think if you have, try to get that knowledge and try to use it to build smaller images or do something else. Don't ignore your Docker ignore. That's probably the easiest way to save as much as you can. Try to use small base images. Python 3.8 Slim is a great useful base image and probably should be the default for all your Python Docker images. Use as few layers as possible, and if possible, remove any build time dependencies. That's it. Thanks.
Yes, thank you, Matthijs. So we're a little bit over time, so I can only take one question. It's a little bit related to the end of your talk, where you have some very nice recommendation what to focus upon. But what is your opinion a little bit more from a data scientist skill set perspective? This is quite heavily engineering. So what do you expect of a data scientist that they at least should know about considering this topic?
Right, that's a good question. I think like the most important one would be your Docker ignore, right? Make sure that you don't copy models in the images that you don't need in production time. Don't copy data that you don't need at production time. And then I would say the second thing would be the multi-stage builds, because there's some nice little tricks that you can do with, for example, running your tests in the builder and then not having them in the runner, which like decreases the dependencies you need in runtime and those kinds of things. And it turned out that that's relatively straightforward as well. The rest of the stuff, probably not super, like, you might run into these kinds of things, right? If you run on very restricted images from a company where you need to sort of figure out like, hey, can I build a wheel of this and can I deploy that myself? But that's starting to get more into engineering territory, definitely.
Okay, cool. Well, thank you very much.